Welcome back to AP Physics. Today we're going to ponder applications of RL circuits and get into LC circuits. Remember, R is a resistor, L is an inductor. Right now our understanding of inductors is that they are coils of wire that set up a magnetic field that opposes any change, any dI/dt. They fight any change in current. Right now on the screen you see two different circuits. The one that is boxed on the left is just a simple circuit with a battery, a switch, and a resistor. The circuit on the right has an inductor in it and a resistor and a battery and a switch. Let's focus on the one on the left. We have the battery, a 2-volt battery. We have a 1 ohm resistor, and then we have the switch. Well, simple Ohm's law. 2 volts over 1 ohm give us about 2 amps of current. So if we throw the switch, we see as soon as we throw that switch, that current immediately pops up to 2 amps, and we get that regular continuous movement of charges. Each one of those little balls doesn't represent a single electron. It represents some quantity of electrons that are moving through the circuit. So then our total current is 2 amps. If we move over to the circuit on the right, should be basically the same. That inductor, if we think about an inductor is basically a long wire made into a coil. So now, if we consider the circuit is pretty much the same as before. 1 ohm resistor, 2-volt battery, and then we have the inductor. Ideally, it's just a long wire of no resistance. So at first glance, we would expect the same thing to occur when we close the switch. Watching what happens though, that inductor sets up a magnetic field that opposes the charge. You don't jump to that 2 amps, you make the circuit sluggish. So if we look at the current values reading there, they're gradually climbing towards 2 amps, but they don't get there right away. Looking at the graph of current versus time, that current increases over time. Now, here's another simulation, just to get the idea of what's going on with an RL circuit. You have the inductor right here, you have the resistor right there, and you have a battery right here. We have a switch, but now we have two different paths, an upper wire there and a lower wire here. If I close the switch, notice what happens on the graph above. That voltage climbs, but it doesn't hit that maximum voltage instantly. So we have reached that maximum voltage, i.e. maximum current. Now if I flip the switch the other way so that the closed loop will have the inductor and the resistor in it, but the battery will be cut out, notice the graph on the top. Now the inductor supplies the energy that is stored in the magnetic field, and it continues to push the current along until it exhausts the stored energy. It makes the circuit sluggish. It fights the change. Okay, now let's ponder our R and L values. If I make L very large and I close the circuit, it extends the time that it takes to be able to reach that maximum. And I'm going to discharge, not discharge, I'm going to let the current decrease. If I make the resistor very small and I close the switch again to complete the circuit to the battery, I make the circuit even more sluggish. So then my inductor has a value of 0.1, which is very high. My resistor has a value of 160, which is very low. A low resistance and a high inductance will give you a very long time constant. If I flip these the other way, high resistance, low inductance, and we flip the switch, notice it jumps up barely any change from an instantaneous. You have a low inductance, you really don't change that rate very quickly. Now let's shift to an LC circuit. So I have a battery, a switch, in the center panel or the center wire I have a capacitor, and in the right hand wire I have an inductor. Inductance units are measured in henries. Capacitors are in farads. Now, with our capacitor and inductor, let's close our switch and see what happens. Now, you may notice when I first closed the switch, there was a flame there. Really should have a resistor there so that you don't get a sudden spike in the current. But what I want to focus on is what is happening with the capacitor and the inductor. Notice that you have an oscillation taking place. The battery is completely taken out of the circuit because the switch is open, but the capacitor plate charges with a certain polarity. Right now the top is positive, and then it discharges. So then you are pushing a current along with a highly charged capacitor. That higher level of current is being opposed by the magnetic field set up in the inductor. As the capacitor discharges, the discharging capacitor, the current reduces. When the current reduces, then the inductor supplies its energy to push the current along, and it charges the capacitor to the opposite polarity. So your inductor is fighting the change. Your capacitor is enabling the change. It is a continuous back and forth, and this is the basis of what is referred to as a simple oscillator or a timing circuit.
Now let's bring all the things together. This summary sheet, it's on Blackboard. It's in the chapter 30 to 32 handouts folder. So you have an RC circuit, an RL circuit, an LC circuit. There's also an RLC circuit. There are different varieties, but this is a basic summary of what the principles are, what's going on, what happens, and then the second page, a summary of the equations. We went fully through RC circuits. Those will be on the AP exam. The RL circuits have been cut off the exam this year, and the LC circuits also. But it gives you an overview. They are very similar in terms of their principles. They're using different fields and different things are happening. Now, what are RL circuits used for? Well, in simple terms, they're used for filters, high pass filters, low pass filters, to be able to filter different frequencies. Now, one last application I wanted to throw in, electrical transformers. Electrical transformers you find on power lines, on telephone poles. You also find more commonly on a lot of devices. For example, your phone charger. The plug is a larger plug, and it has a transformer on it. If you have a charging cord, and your eyes are better than mine because I'm looking at mine, and even with glasses on I can't read the numbers, so you'll have to read yours. There are numbers on there. Your normal outlet supply is 120 volts. Your phone, your computer probably don't take 120 volts. So built into any of those larger unusual size plugs is an electric transformer. The basic idea of electrical transformers is induction. You can see right here and right there, there are the coils on the two sides of our transformer. So you are putting an alternating current into one coil, and then you are inducing an electric current or an EMF in the second coil, and you are stepping up or stepping down that, not current, but voltage. You are stepping up or stepping down that voltage based on how many turns you have. So down here on the diagram towards the bottom, you have a number of turns and a number of turns in your two different coils there. And mathematically, you can work down to the transformer equation, which basically relates the ratio of the voltages to the ratio of the number of turns of loops in the two different coils. So that's the basic principle of an electrical transformer. That is the end of new material. So celebrate, pat yourself on the back. You have made it through all the material in AP Physics. So we will review, we will have a test over this, and we will move into getting ready for the AP exam. Ponder physics.
Do 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 do.